Hello, everyone. My name is Helin Tao from the University of Bonn and Lamar Institute. I'm honored to present our research with the title SLCF-Net, Sequential LiDAR Camera Fusion for Semantic Scene Completion using a 3D recurrent unit. This work is a cooperation with my advisor, Professor Sven Benke. As we all know, the perception system can only measure the surface that can be observed in the scene. So it always suffers from the missing geometry and semantics caused by occlusion. But with the deep neural network, we can estimate the occluded geometry and semantics. By analyzing the data modality, we found the camera can provide rich semantic information in RGB image, and LiDAR can provide precise depth measurements. They show strong complementary effects for semantic scene completion, and they are always available in normal autonomous vehicle frameworks. Our approach aims to jointly estimate the complete geometry and semantics from an RGB image and the corresponding sparse LiDAR depth map. The pipeline can be divided into 3 parts. In the feature extraction part, we employ the 2D unit to extract semantics from the RGB image and design a depth condition pipeline fueled by depth sequencing to predict the dense depth priors. Afterward, we design a GDP module which back projects the 2D features into a 3D volume using the depth priors. The 3D features are then fed into a 3D unit which estimates a dense semantic scene. Furthermore, this 3D unit keeps hidden features, enabling it to learn information from the previous frame. 2 highlights of this pipeline are the GDP module, which back projects 2D features to 3D space, and the 3D recurrent unit, which learns temporal information. The GDP module is short for Gaussian-decay Depth-prior Projection. Assuming there's a 2D feature located at pixel P, it can be back projected along the line of sight. All the voxels passed by the line of sight have a potential relationship with this feature. With the depth prior, the P hat is considered the most related point, and the weight is decayed with the increased distance to the P hat. So we describe this weight with the Gaussian decay function. That is the core idea of GDP module. For the 3D recurrent unit, we aim to utilize the information from previous frame. So we design a hidden feature that stores the previous information and propagates to the current estimation. There's an overlap area between neighboring frames. With the known pose of each frame, we propagate the feature in the same global positions via alignment and concatenation. We evaluate our approach in SemanticKITTI datasets and get strong results. Specifically, SLCF-Net outperforms those baselines on both scene completion and semantic scene completion tasks. Besides the number, you can also see the visualization of input and output and comparison with other leading SSC approaches. We labeled shadow areas which are located outside the field of view. And in the estimation, we visualize the unknown regions at 20% opacity. We do ablation studies on variance of GDP and also the initialization of the hidden layer. You can check more details in our paper. In summary, the main contributions of this paper include the SLCF-Net. It's a novel SSC method that fuse 2.5D sparse depth maps with 2D RGB images. And the GDP module, a Gaussian-decay Depth-prior Projection method for projecting 2D features into 3D. And the mechanism that propagates the feature from the previous frame to the current frame based on the alignment and the concatenation. Thanks for your attention. I hope to see you in the ICRA2024.